Anybody have any questions about homework problems or anything like that? Yes.
I just have like quick question.
Yeah.
Last Tuesday, I didn't come to class because I don't know, I read the announcement.
Oh, yeah.
So we did quiz. Do just like.
Yeah, I'll put a quiz in there and give everyone full credit.
Nice. Okay.
We didn't take it anyways, but everyone could use a little boost. Full credit for surviving the election. If there's a big election that day.
Number 11.
Yeah.
I don't know. I didn't end up with the right number of equations.
Do you have the question with you? Oh, yeah. Okay. Okay, pin. So there's, and one here. And then there's a bunch of dimensions. And then there's one vertical dimension. Okay, so I think that's everything. So let's call these pieces 1, 2, 3, 4. And let's call the joints well, I guess, yeah, let's just name the joint. So I'll call this one A, B, C, D. And then what we're trying to figure out is what this force R is that has to keep this in static equilibrium. Or if you apply this force of 50 newtons to each handle in a way that this is in static equilibrium, what force R are you applying to human bone? Well, there are a couple ways to simplify this if you're sort of clever about, you can cut this down to half a problem if you recognize that everything's going to be symmetric about a horizontal line, but let's not do that because you know how much I hate thinking. Let's just go through it like a little human robot. Mm-hmm.
Does it matter if it's like middle of the, like at the tip of the?
It does. That's what that 1 centimeter is supposed to measure, so it should be in line with this line.
Is this the homework in the structure problem?
Yes.
Okay.
Okay, so we have a downward force of 50. Pin joint at A. So that's a force on 1 by 2. And then we have another pin joint here that's the force on 1 by 3. I think I'm going to put the about point here. So the about point is at that joint A. To get from A to where that 50 Newton force is applied, it's 10 centimeters in the positive x direction. So 0.1, I'm translating to meters. And, well, the height doesn't matter because this is a vertical force. So you can move it anywhere along its line of action. I'm just going to put it at 0. Everyone follow what I'm talking about there? I didn't give, there are no dimensions that say the height difference from the joint A to up there where that force is applied. But the reason that's not given is because you can move this 50 Newton force anywhere along its line of action, which means you could put it at a height of 50 meters, 1 meter, 0 meters. It's not going to change the problem.
The y direction.
The y position doesn't matter because of the direction of that force. Yeah. And the force is 0, negative 50. And so the cross product is negative 5. And now we're at the joint A. There's no row vector. The force is F12, x and y. Cross product is 0. And then the joint B, that is up 1 centimeter and over 1 centimeter. So the row vector is negative 0.01, positive 0.01. Cross product, the force is F13x, F13y. And the cross product says negative 0.01 F13y minus 0.01 F13x. So this gives our first 3 equations. And for variables, we have 4. And those are F12 vector and F13 vector. And then we'll go to member 2. Which one is that? The bottom one. So we have a 50 Newton force. At A, we have the negative force on 1 by 2. And at the joint C, we have the force on 2 by 4. put the about point at A again. So the 50 Newton force is at 0.10. The force vector is 0, positive 50. Cross product is positive 5. Then at A, row vector is 0. Force vector is negative F12x, negative F12y. Moment is 0. And then at whatever that is, C, that is negative 0.01, negative 0.01 for a row vector. Force vector is F24x, F24y. So cross product is negative 0.01 F24y plus 0.01 F24x. We get 3 more equations, so now we're at 6 equations. We've added one new variable, one new vector variable, so 2 new variables. So 6 variables. That's F12, F13, and F24. And we don't usually have this happen, but we could solve for what we have right here. That's not everything yet, but we could do it as an intermediate step and then not have the big matrix at the end if you want. I still just make the big matrix at the end. And then we'll go to member 3. We have the force R there. Here we have the force on 3 by 4. And here we have the force on 3 by 1. That's negative F13. I'll put the about point down there. So that force F13 is at positive 5 centimeters, positive 1 centimeter. The force is negative F13x, negative F13y. Cross product is negative 0.05 F13y plus 0.01 F13x. Then the force F34, the row vector is 0. Bless you. No moment. And then this force R, the row vector is negative 1 centimeter. And then we don't care about the y position again because of the line of action. I'll just put that as 0. The force is 0R. Cross product is negative 0.01R. And so for equations, we're up to 9. For variables, let's see. The only one we added is 3, 4. So now we have 8 variables. Those are F1, 2, and R, yes. F1, 2, F1, 3, F2, 4, and F3, 4. And R. We just talked about that. Okay, and then are there any other variables that we haven't introduced yet? Yeah, I guess, no, there's not, right?
Everything else would be satisfied by,
Yeah, so everything else is going to come in through Newton's third law.
yeah.
So there's no point in, like if we do the other 3, what this says, if we isolate the last body, we're just going to come up with 3 equations that are already represented. They're linear combinations of the 9 equations that we already have. And so we can do it now.
Any solutions online for this problem?
Yes.
Added another full force vector in there?
Yes. So,
And then another like
okay.
upward one?
So here's what's weird with this one. We don't get too many where we don't isolate every body, right? So what's going on with that? Well, this problem, the way it is drawn here, there's nothing restricting its rotational motion or translational motion. And that's why we got the weird thing where we didn't have to isolate the last body. There's like these extra degrees of freedom that we don't normally see. Usually the thing is locked to the ground in some way. You know what I mean? This is just hanging free in the air. And so what I did in my solution was I said, basically I locked it in place. I said, let's say this pin joint attaches it to like the wall.
Sure.
And let's say that this one, because of symmetry, as this opens and closes, this pin will change its horizontal position, but it won't go up and down. And so I locked this to the wall to limit translation. And then I put this in a pin and slot joint, basically, that could slide along the wall. And what that did was restrict those extra degrees of freedom. But what it did was it introduced 3 new variables that then we had to solve by isolating the 4th body.
Sure.
Um,
So it's just
Sort of unnecessary
it's
work.
not necessary
But
step. Okay.
when I looked at it, that's what made sense. I looked at it and thought, like, yeah, that thing can move and rotate and stuff. Let's fix that, you know. And so either one of those 2 approaches will work.
Okay. The last one to the left, you don't have to isolate it, right?
No, because if you isolated it, you'd see that you didn't introduce any new variables.
Yeah.
And so then you'd have 9 variables, 12 equations. And that means you have to throw away 3 equations anyways. You can choose which 3 to throw away,
Oh, okay.
but
So it's unnecessary to isolate it.
unnecessary, right? We already, after 3 bodies, we already have all our variables. We can already solve for them, so there's no point in going on.
Okay.
Yes?
If you still get the same answer if you do all the 12 questions?
Yes.
equations?
If you enter a system of 12 equations for 9 variables into your calculator will say, give me 3 fewer equations. So what you need to do is just pick 9 of the 12, which means you can skip the step of isolating the last body. You already have 9 equations. Yes? If we have what? If the mass was given, I don't think so. I don't think it would change it, actually, in this case. The only thing that makes this problem weird is that is that these plier things are floating in space. And so there's nothing restricting its rotation and its translation. And that's why we have 3 fewer variables than we're used to in a structures problem like this. In my solution that's posted online, I did something that added 3 more variables and made it like a structure that we're used to dealing with. But you can also just do it with fewer variables. Yes?
You end up with a similar phenomenon where you end up with 3 variables and 3 equations on number 9 as well. As in, we're midway through the problem you can solve for
Yep.
stuff.
That's
You
right.
end up with something like that on number 9 as well.
Oh, number 9 too?
Yeah.
Yeah, sometimes it happens.
Yeah.
I usually don't, I don't even like really look for the most part, because I just wait till the end and solve it, you know. It doesn't take that much time.
But a big matrix leaves so much room for error.
What does?
A big matrix just
It
leaves
does,
so
you're
much
right
room
about
for
that.
error.
Any other questions about that one?
I have a question, but not related to this
Okay.
problem. So basically, I still make mistake if there is distributed load going down, and there is like a beam, and we're doing structural problem. So we treat the distributed load like centroid. We find like the x direction. We find the centroid of the area of the distributed load.
Yep,
Oh, okay.
that's right.
Yeah, because I did like find the middle of the beam. So
Okay. Yeah, so you do it at the centroid of the distributed load.
Okay. So
If it's in a structure, you do it the same way as if it's just a rigid body problem with a centroid.
So
with a
if like it's triangle distributed load, we do it. We find the area of the triangle for the force and the centroid. We find it like in the centroid problem, like
Yes.
we find the centroid. Like
Exactly.
Yeah.
Yep.
That's the explanation. Okay, thank you.
Yep. Any other homework questions? Yep.
For number 9 as well, I
Mhm.
think your solution online is really
Yeah, probably.
I can show it to you after class if that would be easier.
Okay. I think somebody did mention that
Okay.
there was a negative sign missing somewhere. I don't remember if it was that one or. Hopefully it was that one.
I'll talk to you after class.
Okay. Any other homework questions?
Number 6.
6. Oh, yeah, that's a weird one. This is supposed to be like a nutcracker or something. Anyways, there's some object in there, and we're trying to figure out how much force this contraption is applying to that object. Force P there. 60-degree angle there. -20-degree angle there. Um, .200 millimeters, so 0.2 meters. 0.4 meters there. And this angle is 15 degrees. So now I think maybe we have everything. So let's call the big outer member 1, this little thing 2. So what we can do is we can think of this as just we can think of this as fixed to the, not fixed, but a pin joint connecting this to the ground, and then just do this as a 2-member structure, figure out what that reaction load is. And once we have that reaction load, we can think about, then we can go on and think about this. To me, that's the most reasonable way to approach it. So we've done problems like this many times. It's sort of the simplest version of a structure you can have. And so let's do that, and then we'll go from there to figuring out what the force is that this third piece applies to that object. Okay. So, well, let's not go through like all the math and stuff on this. Anybody have any questions about, so once we get to this, doing the math to calculate, if I call this joint A and this joint B, doing the math to calculate that reaction at B is something we've done a bunch of times, right? So what happens once you get that? So solve this structure for the reaction at B. And now isolate that third piece. I'll number that 3. So what's going on with that? Up here, there's a force. So we calculated the force on body RB is equal to the force on body 2 by body 3. And so this force now is the force on 3 by 2. And then we also have a force from the sides that's holding it, keeping it from accelerating horizontally. I'll just call that R. And then finally we have the force F that we're trying to find. So Newton's second law says negative F3 to X, negative F3 to Y, plus R0, plus 0F is equal to zeros. These aren't variables, right? These are known from before. And so that force F is just equal to F3 to Y, which is known. And then I guess if you want the force, that's calculating the force that that little piece is applying to member 3. Then if you want the force, well, that's just giving a variable. But if you do this as a vector, then you have to switch the vector direction so that you're calculating the force on the little object by member 3. But this variable, this variable f gives you that magnitude.
By Newton's third law, wouldn't it just be the negative of that?
Don't use Newton's third law on variables that way, you know what I mean? So what Newton's third law says is if this is if that's the force on the object by 3, nope, that's not true. That's the force on 3 by the object. Then this is the force on the object by 3. Any other questions about that one? You could do this whole thing as a structure. So you could just do it as a 3-piece structure where that little body 3 is connected to a pin joint here. Its horizontal motion is restricted by a force R, and there's a force F pushing up on it, and solve the whole thing as a single structure. This was just the first way that occurred to me to do it. But Any other homework questions? This is yours, right? Okay, so now let's talk about internal loads.
Number 10 is actually asking for internal loads.
Oh, then that should not be in that. Okay, that's just in the wrong set of practice problems. Maybe we'll come back to internal loads.
Okay, yeah.
Okay, so yeah, in the homework that I assigned, it says something about internal loads. We haven't done that yet, so skip that. You can still solve the structure, though. So still do the structure problem, just don't do the internal loads. Okay, so here's the idea of internal loads. And you can think of this as the start, or maybe continuing down the path, the next step, but of an important area in mechanics. And that is, will it break? And second, where will that break start? So far, all we've calculated is external loads on objects, and it's sort of natural to think that if you want to figure out where something's going to break, you look for where the external loads are biggest. But that really isn't how it works. So think about this. This is like a thought experiment. These are human hands. Okay, and imagine you're holding a stick. A free body diagram of the stick looks like this. Your thumb is applying a force here, and your fingers are applying a force like this that counteracts it. So those make a couple. And then over here, your thumb applies a force F, and your fingers apply a force F. And so if you're just assuming that this thing is most likely to break where the external loads are maximum, you would think this break would happen in one of these 4 spots. But that's not what would happen if you do this. Do it right now with your pencil. The break is going to happen somewhere between the 2 thumbs. And there's no way to calculate where, but it's not going to happen over by the external loads. It's going to happen in here. The break starts here.
Is it in the middle, like in the?
Not necessarily. You have to know more about, you need to know more about the materials and things to calculate where between these 2 Fs, but you do know it's going to happen somewhere between these 2 Fs, between the 2 thumbs. So what's going on there? Well, external loads aren't what causes a break. A break happens when 2 adjacent pieces of material are trying really hard to get apart. So the break starts where 2 adjacent pieces of material are fighting to get apart. Another way to say that is, so in other words, one piece of material is applying large loads to an adjacent piece of material. And that's what internal loads are. Internal loads are the loads applied to a piece of material by the adjacent material. So if you calculate where those internal loads are the biggest, that'll help you locate where the break is going to start. Okay, so let's think about what that calculation means. So these are the places with large internal loads. And the idea of calculating internal loads is it's actually pretty simple. Like we could think through it somewhat right now without learning any new techniques or anything. I'm just going to go through first with an example, and we'll end up changing a couple things, changing a sign convention and whatnot, but I want to sort of motivate that. So let's say that we have this piece. We have this beam. (500 Newton forces applied downward on the 2 ends, and then for this to be in static equilibrium, there's also a 1,000 Newton upward force acting in the middle. let's say that this is 1/2 meter. And this is 1/2 meter. And just arbitrarily, let's say that we want to calculate the internal loads at this point, halfway between, so this distance is 0.25. And so here's what we're going to do. We're going to calculate the loads applied to the material to the left of the red line by the material to the right of the red line. So I'm going to draw a free body diagram of that left piece. And I always say not to do this, but in this case I think it might be sort of helpful to, so this is the left piece. And this is the whole beam. We're not isolating the whole beam, though. You know, that's the beam with the downward force there, the upward force there. The part we're isolating is just this. Does everyone understand what I'm talking about? And so if we're isolating that black piece, we're just isolating this piece here. We know that there's a downward force acting on it. If we go around the boundary looking for contact, there's also obviously contact where we've drawn this, chosen to make a cut between the piece we're isolating and the rest of the beam. What kind of loads are applied? I mean, think of it as a joint. What kind of joint is it between the stuff we're not considering and the stuff we are considering? It's a fixed joint. Yep, exactly. And so at a fixed joint, you expect there to be a full vector of forces and a couple. And so I'm going to call this force vector R, and this couple MR for reaction moment. And the reason that those are a couple and a force vector is because that's a fixed joint. And so Newton's second law says 0, -500 plus Rx, Ry is equal to zeros. And then I didn't write out rho and F and M. We could do it for this. This is just a rigid body problem, but since the beam is horizontal and all the, we can just break it up into horizontal and vertical components. It's not too hard to just do in your head. So let's take this as our about point. And then the moments produced around that about point. So what's going to produce, so let's think first about the moments. Let's do the easy one first. MR, just add that in, that's a couple. Is the horizontal component of R going to produce any moment around that? No. its line of action goes right through it, is the vertical.
Yes.
Yes. And so what's the moment arm of that vertical component of R? 0.25, the length of that. And then would an upward force of, Ry, that upward force, would it cause a counterclockwise rotation or a clockwise rotation if this is like a hinge? It would be counterclockwise, so that moment's going to be positive. So it's going to be 0.25, the moment arm, times Ry, and then all that's going to be positive because it's counterclockwise.
But why you choose the above point to be at like 500? Could we have chosen to be at like
Yeah, we could have. There's going to be a reason in the future that we're going to put it there, and so I'm putting it there now. But yes, you're right. It would make slightly more sense to put it over here, but you can put it anywhere you want. You have a question, Daniel?
Yeah, so you did it around the 500 point. I'm a little confused about why MR is transferable over there.
Couples, you just add on couples, no matter where the
Acting around.
the big thing with couples is no matter what your about point is, that couple is the same. Remember when I first introduced couples, I went through that proof that showed no matter what your about point is, it disappears from the calculation of a couple. And so no matter what your about point is, that couple adds on in exactly the same way. Okay, so we have three equations for three variables, and that tells us that R is equal to 0, 500. And MR then is equal to negative 125. This is Newton meters, this is newtons. And those are the internal loads applied to the left piece. There's something, though, that isn't ideal about this. So, however, this vector sign convention that we're used to leads to an undesirable thing. And that is, what if, so we did this to calculate the internal loads at that red line. What if we had calculated the loads applied to the right piece by the left piece? Well, it's just a Newton's third law thing. All those signs, all the values would be the same, but all the signs would be switched. That's just Newton's third law. So we would have gotten an R vector that was equal to 0, negative 500, and a couple vector that is 0, 125. Not 0, 125, just 125.
But why is this Newton's third law because the distance between, I'm just still confused because the distance between
Well, so like the force on the left piece by the right piece
Oh, okay.
is equal to the negative force on the right piece by the left piece, and MLR is negative MRL. Yes?
Wouldn't that moment have to be different because you're adding another force in?
It's no different. Numerically, it's just the sign that's different. Newton's third law says that has to be the case, and if we went through the calculation, you'd see that's how it would work out. And what we'd really like is we'd like these values of internal loads to represent what's happening at that line. At that red line. Independent of how we do that calculation. Okay, we want to be able to say at that red line the internal loads are this, without saying we did it, we calculated it by isolating the right piece or by isolating the left piece. Okay, and so in order to fix that little problem, we're introducing a new sign convention. That the danger is that this new sign convention kind of obscures the simplicity of this idea, that we just assume there's a fixed joint, apply the loads that a fixed joint applies. But here's the new sign convention. We treat the line where we want the internal loads as a sliver of material. And if we're working on the right side of the sliver, a horizontal force, a positive horizontal force is called T, and it acts to the right. If we're working on the left half, it points to the left, and we call it T. For vertical forces, if we're working on a right face, we call a positive vertical force V. If it points down, and on the left half, we say V is positive if it points up. And then finally, for the couple, we call the couple M positive on the right face if it acts counterclockwise, and on the left face we call it positive if it acts clockwise. So what this does is, no matter how we do this calculation, a value of T, a value of V, and a value of M match. Okay? If we did it by isolating the left piece, we'd get the same values that we would isolating the right piece. This is called tension. Negative is called compression. This is called shear force. Whether it's positive or negative, you call it shear force. And this is called the bending moment. Okay, so let's do this. Let's do this calculation again using this new sign convention. So our free body diagram of that left piece we have a downward force of 500. And now instead of, so it's still a fixed joint at the right side of the piece we're isolating. But instead of writing that as a force vector and a couple, we're going to write this as a tension, a shear force, and a bending moment. We haven't made any fundamental changes to how we're treating that load. We still have a horizontal and a vertical force and a couple. We've just changed the sign convention. Okay, so Newton's second law says 0, negative 500, plus this force T, this tension force. What are the components of that? It's in the positive x direction, so that's just going to be T0. And then this V is in the negative y direction, so that's going to be 0, negative V. Those are equal to 0. And this tells us that T is equal to 0 and V is equal to negative 500 newtons. And now let's think about the moment equation. Again, I'm going to, you might think it's a better choice to choose the about point over at the right, and that makes sense in a lot of ways, but because of what's coming, I'm going to put it here. Okay. Mathematically, you can put it anywhere you want. So what's the moment produced by the 500 Newton force? 0. What's the moment produced by the tension? 0. What's the moment produced by V? Well, we have a moment arm of 0.25, a force of V, so the magnitude is 0.25 V, and now would this cause a clockwise or counterclockwise rotation around this point? Clockwise, so it's negative. So that moment is negative 0.25 V. And like I said before, you could just as easily write out your row vector, your force, your moment, calculate these the way we have in rigid bodies before. It's just that these are sort of easier to eyeball once you get used to it than the other ones we've done. And then the last thing that produces a moment is that couple M. That's independent of the about point, so you just add the M. We know that V is negative 500, so we'll plug it in here, and we get 125 plus M equals 0. So M is equal to negative 125 Newton meters. Any questions about that?
So if we're isolating the left side of the beam, we're treating like V as it goes down is negative and up is positive.
Yeah, so if we were working from the other direction, yes. If we were working from the other direction, we'd have the downward force of 500. We'd have the upward force of 1,000. And then these internal loads would be T this way, V this way, and M this way.
Oh, okay.
And if we went through that calculation this time, this isn't what happened before with the vector sign convention, but with the new sign convention, we'd get this T is equal to 0, this V is equal to negative 500, and this M is equal to negative 125. With that new sign convention, we eliminated the dependence on how you calculate those internal loads.
So your tension and your shear, like let's say this was a horizontal and vertical,
Mhm.
your tension would be in the Y.
We're always going to make it horizontal. So if you're doing it for something vertical, we're going to translate that into looking at it horizontally.
Okay.
But doesn't Newton's third law switch sign?
No, it doesn't, because we're not using the vector sign convention anymore. I mean, Newton's third law still applies, you know,
Yeah.
but we've chosen this new sign convention that sort of gets around it. And so the whole reason that I did this example in the different ways is to show, like, we have this new funny sign convention. And where does it come from? It comes from wanting to have independence, wanting those internal load calculations to be independent of how you do the
So
calculation.
like tension, state tension, the T is state T. It's not
Right.
like F1, 2,
That's right.
F1.
Exactly.
Okay.
Yep, exactly. That's what we have now.
Yeah. Thanks.
So this would give the exact same values for T, V, and M. Not M factorial. That's an exclamation point. Remembering these sign conventions, well, I can't help you with tension and shear force. You just have to remember those. But the bending moment is easy to remember. If you bend a beam like that, it's positive. And if you bend it like that, it's negative. All right, so we're getting there. Is that it? Are we done with internal loads? Well, what we would like is that really is all there is to calculating the internal loads at a single point. But the problem is we usually want to calculate the internal loads across a whole beam to figure out where it's biggest and smallest, you know. So the last step is we want a way to calculate the internal loads along the whole beam. Okay, so let's go back to the example that we just did. This beam is 1 meter long. We calculated the internal loads at 1 point. So how many points do we have left? Well, it's infinite, and it's countably infinite or uncountably infinite? Uncountably, which means we can't even really put a list together. So all that seems pretty bad, you know, like it's going to take us a pretty long time to get through this beam. We need another approach. Okay?
This probably will take more than like a year.
Yeah, well, yes, indeed it would. But I mean, it's not a totally unreasonable approach to think of it as like the way a numerical problem works and just say like we'll break it up into 50 pieces or something and do what we did here at 50 different spots. But that's not what we're going to do. And so, the way we're going to do that is we're going to identify places where the free body diagram of the beam changes fundamentally. Identify places where, so let's say instead of fundamentally, let's say qualitatively. So identify places where the free body diagram of the chosen piece of beam changes qualitatively. All right, so let's go back to the example that we've been using. $500 newtons down at the two ends and 1,000 up. And I'm going to always do my cuts. I'm going to always take pieces that start all the way at the left and the right side works its way to the right. So let's start out with a piece like this. So we have 500, and then over here we have T, V, and M. Now let's see what happens if we isolate a little bit bigger piece. We have 500. And we have T, V, and M. Those T, V, and M values are going to change depending on how long that piece is. But all of the loads acting on it can be represented the same way. But that changes once the right side crosses this 1,000 Newton force. So now we have the 500, and we have the 1,000 up, and we have T, V, and M. And if you include a little bit bigger piece, you have the 500, you have the 1,000, and you have T, V, and M. So these two are qualitatively the same. And these two are qualitatively the same. But these two are fundamentally, qualitatively different than these two, okay? Because there's a new force acting on those second two that wasn't acting on the first two. Yes?
You can't have a situation where the rightmost 500 Newton force would be had as well?
We will not do that. That's right. You could do it, but if you did, then you would just be calculating the external loads. You know what I mean? If you picture what's happening here.
Yeah, because it would have no bending moment.
Yeah, That's right.
Okay. Can you even include that if that 500 Newton force is truly on the edge of the beam?
We never will.
Okay.
Yeah, if you did, it would just be a rigid body problem, and you'd just be calculating the external loads.
Okay.
There's basically the same way of doing it. Like,
Yeah. So here's what we're going to do. So, okay, so this beam requires 2 cuts. Cut 1 is going to look like this. We have the 500 Newton force. We have the internal loads. And the length of this beam is some x value that falls into the range between 0 and 0.5. Okay? If x is bigger than 0.5, we've gotten to the other qualitatively different configuration because the right side of the beam has crossed over to now has to include that 1,000 Newton force. So Newton's second law says 0, negative 500 plus T negative V is equal to zeros. So T is equal to 0, V is equal to negative 500. And the moment equation, we're going to calculate our about points around that left point. There's no moment produced by the 500. Is there a moment produced by the tension? No. The moment produced by V, what's the moment arm? X, exactly. And would that force V cause a clockwise or counterclockwise rotation? Clockwise, so negative Vx. And then plus M is equal to 0. And so now if we're using this to calculate the bending moment is equal to Vx, which is negative 500x. So as you're looking at points over the left half of that beam, the tension is 0 the whole time. The shear force is negative 500. The bending moment varies from, depending on what x value you're looking at, you get a different value of that bending moment. And now we'll go to the second cut. This is the one that represents that second qualitatively different configuration. So we have 500 down, 1,000 up, internal loads, this distance from the left end to the 1,000, that always stays the same. That's 0.5 meters. But the distance from the left end to the right end is now an x value that has to fall somewhere between 0.5 and 1. If the distance, if the distance from here to here is less than 0.5, then we're not looking at this configuration. We're looking at the one without the 1,000. So this way of looking at it is only valid if the right end is at least 0.5 from the left end.
For a second.
What?
Oh, I forgot how
Oh, yeah.
open intervals work.
Yes. So, and actually, every interval we're going to do is going to be open. We're not going to ever analyze what's happening right at those point forces. Okay, so let me just finish this. So Newton's second law says 0, negative 500, plus 0, 1,000, plus T0, plus 0, negative V, is equal to zeros. So T is still equal to 0. V is equal to positive 500. For the moment equation, we'll use our about point at the left. So the 500 Newton force doesn't produce a moment. Does the 1,000 Newton force produce a moment? Yeah, and what's its moment arm? 0.5, and is it clockwise or counterclockwise? Counter, so that's going to be positive 0.5 times 1,000. And then the T never produces a moment. We always add on the M. And the V always occurs as minus Vx. The moment arm is X, the force is V, and it would produce a clockwise moment. And so M is equal to negative 500 plus Vx. So plug in what we know for V, and you get M is equal to negative 500 plus 500x. So T is pretty uninteresting. That just stayed 0 the whole time in this problem. That's obviously not always going to be the case. But the other two, if you want to get a sense of where we're worried about this beam breaking, you can plot these out. So shear force, there's X, there's the midpoint, there's the end. Over the first half of the interval, V was negative 500. Over the second half, it was positive 500. So the graph looks something like this. And the bending moment looks something like, it reaches a peak of negative 250 at the midpoint, and it's a linear function, piecewise linear function like that.
But why does it break? Like, is it at 0.5 break?
Yeah. Oh, where does it break? So that's a little more complicated question than this. But if the piece was the same material all the way through, the same thickness all the way through, you would look at this and you would say, there's no tension anywhere, so that's not a factor. The shear force has the same magnitude everywhere, so that's not a factor, except right at the midpoint. And so the only thing that varies is the bending moment, and that is the biggest in absolute value the closer you get to the midpoint. And so we'd be concerned about this breaking near the midpoint. Okay, that's all.